Okay, so let's get into this. I find this paper so interesting because we're used to thinking about AI in tasks where there's a really clear right or wrong answer.
Right. You write a piece of code, it either runs or it throws an error.
Exactly. Or you do a math problem, it adds up. You get that feedback instantly.
But uh, real science doesn't work that way
Yeah.
at all. If you're trying to, say, develop a new drug,
You don't get an error message in 2 seconds.
you get a failed experiment 6 months and maybe millions of dollars later. And that's the feedback loop problem. This paper, Training AI Co-Scientists Using Rubric Rewards, really digs into.
This is from the team at Meta Superintelligence Labs, and what I love is their pivot. They just sidestepped the whole problem of simulating experiments.
Yeah, they couldn't simulate the doing of science, so they decided to simulate the planning of science.
Which is kind of like a PhD advisor and their student, right?
That's a perfect analogy. The student brings a plan, and the advisor, constructively tears it apart before anyone touches a beaker.
You didn't think about this control variable. Your sample size is way too small, that sort of thing.
Precisely. So to automate that advisor, they went data mining. They took thousands of published papers from ML, from medicine, from architecture.
And they reverse engineered them. What does that actually look like?
So for every single paper, they extracted two main things. First, the big research goal. What was the problem they were trying to solve?
Okay.
And second, a goal-specific rubric.
Like a grading sheet, a checklist of what that specific successful paper actually did to solve the problem.
Exactly. It's the cheat sheet of what good looked like in that context.
So how does that become a training exercise for an AI?
This is the really clever part. They set up a system with a student AI and a judge AI. The student gets a goal and has to write a research plan.
And the judge grades it using that rubric.
Yes, but here's the twist. The judge has what they call privileged information. It gets to see the rubric, the answer key.
But the student doesn't.
The student has no idea what's on the checklist. It just knows it failed. It has to learn through trial and error how to generate a plan that satisfies a judge who knows all the secrets.
So it's learning to anticipate what rigor looks like. It's learning the rules of good science without ever being shown the rule book.
It creates what they call a generator-verifier gap. It teaches the model to self-correct.
The big question then is, does it actually work? Can AI trained this way plan science that humans think is good?
It can, and it's pretty impressive. They put the plans in front of human ML experts, and they prefer the rubric-trained models plans 70% of the time.
70%. That is a massive leap over the base model.
It is. The experts call the plans sounder and more useful for graduate students, but honestly, that's not even the part that really got me.
This is where it gets weird, right? The cross-domain skills.
Yeah. So they trained the model heavily on medical papers. So you would expect it to get really good at planning, clinical trials.
And it did.
It did, but it also got significantly better at planning physics experiments.
Wait a minute. How does reading about biology help you design something for a particle accelerator? The domains are completely separate.
That's the whole point. It suggests the AI wasn't just memorizing medical facts. It was learning the underlying grammar of the scientific method itself.
So how to structure a hypothesis, how to isolate a variable, the logical flow.
Exactly. That abstract structure is universal. Whether you're studying cells or stars, the shape of a rigorous experiment is often very similar.
That is a wild idea. It's not learning the content of discovery, it's learning the process of discovery.
And the performance backs it up. This training method let a pretty moderately sized 30 billion parameter model compete with giants like Grok 4 thinking.
So it wasn't the top dog. I think GPT-5 thinking was still ahead, but it closed the gap significantly.
It shows it's not always about having a bigger model. Sometimes it's about better training. It gets us closer to a true AI co-scientist.
Not a replacement, but a partner. An advisor on your shoulder that's on 24/7, making sure your plan is solid before you spend the next year going down a dead end.
Invaluable. But it leaves us with a really provocative final thought. If training an AI on medicine improves its physics planning,
Then the scientific method isn't just some human tradition.
it suggests it might be a more fundamental universal algorithm for seeking truth. And if an AI can master that algorithm,
Then the barrier to making discoveries in any field could drop dramatically.
a universal language of discovery.
That is definitely something to think about. Thanks for diving in with us. Okay, let's unpack a paper that dropped, I think it was back in December 2025. It's from researchers at Meta and Harvard.
That's the one. Confucius Code Agent.
Right. And honestly, The whole premise is a little humbling for the big AI model creators.
It really is. I mean, the entire industry is so obsessed with brain size. Is it GPT-5? Is it Claude Opus? But this paper argues we've kind of hit a ceiling. Raw intelligence isn't the bottleneck anymore.
It's the scaffolding.
Exactly, the scaffolding.
That's the key word for our deep dive today. We want to figure out why the environment around the AI seems to matter more than the AI itself, especially for fixing really complex software bugs.
Because right now, most coding tools just fall apart on big real-world projects. They suffer from what I'd call the genius in a chaotic office problem.
A chaotic office.
Yeah, you could hire the smartest person in the world, but if their workspace has no filing system, constant noise, and zero project history, they're going to fail. That's AI coding today.
So how does this Confucius code agent CCA, how does it clean up that office?
It starts with a completely new idea. The researchers call it AX, Agent Experience.
Okay, so we know UX is for users, DX for developers. Why does a machine need an experience?
Because machines get overwhelmed by noise, just like us. Most tools just dump raw, messy terminal logs into the chat. That's a terrible AX. It just confuses the model.
So CCA creates a clean workspace.
A clean workspace. It distills all that raw data into organized, structured updates. So the AI focuses on the signal, not all the noise.
That makes a ton of sense. It's like getting a clean expense report instead of a shoebox full of receipts. But that doesn't solve the memory problem, does it? The context window.
Right, you can't fit the whole history of a huge project in there. And usually, tools just start deleting the oldest messages to make room. CCA doesn't do that.
This is where it gets really interesting. It has something called the architect agent.
Yep, and instead of deleting the history, the architect compresses it. It's constantly summarizing the conversation into structured data.
Like what? What kind of data?
Things like, what are our current goals? What decisions did we just make? What are the next TODs? It creates a dynamic strategy document, not just a transcript.
So it allows for what they call long horizon reasoning.
Exactly. The AI can remember a key decision from 3 days ago without needing the exact dialogue in its active memory.
That's powerful. But the part that really jumped out at me was the note-taking agent. That feels like the actual killer feature here.
Oh, it is. Standard AIs are stateless. They reset every time you close the session. Total amnesia.
Right.
CC's note-taking agent runs the background and writes persistent markdown files.
And it's not just jotting down the final answer, is it?
No, and this is the critical part. It writes down what they call hindsight notes. It documents the failures. If the agent tries a fix and gets an error, it writes that down.
So if it runs into the same bug 2 weeks from now.
It reads its own notes. It sees, oh, wait, I tried this last time and it crashed the build. And it just avoids making the same mistake. It's building institutional knowledge.
So does all this actually translate to better performance? What do the numbers say?
The numbers are stark. On the SWE-Bench-Pro benchmark, which is the gold standard for these tasks, CCA hit a 54.3% resolve rate.
And how does that stack up against, the big commercial models?
It beat them, including systems running on Claude Opus 4.5. But here's the real aha moment. A weaker model, using this better scaffolding, actually outperformed a stronger model with bad scaffolding.
Wow, so that proves the hypothesis. The environment really does beat raw IQ.
Completely. The paper has this great case study on a PyTorch bug issue, #161356. It's about CUDA memory allocation.
I saw that. The fix was actually pretty simple, wasn't it? Just removing an assertion check that was too strict.
Dead simple. And CCA acted like a senior engineer, kept its context, saw the check was the problem, and just removed it. Clean, efficient.
And the competitor. They used Claude Code for the comparison.
They did. And its approach was a total mess. It used multiple sub-agents that were supposed to delegate tasks, but they didn't have that shared, structured context.
So they all got confused.
Totally confused. They lost the thread, overanalyzed the problem, and proposed this massive, over-engineered rewrite that wasn't even necessary. It was a committee of juniors not talking to each other.
Versus one focused senior with a good notebook.
That's the perfect analogy.
So what does this all mean for you listening? It seems pretty clear that success in AI engineering isn't just about waiting for a bigger brain to come along.
It's about building better tools, better memory, better scaffolding. And there's a provocative thought to leave you with. CCA uses a meta-agent to build, test, and improve itself based on its own performance.
So it learns from its own notes.
It learns from its own history.
Yeah.
So if these agents can now maintain a persistent identity, Are we finally moving away from the era of stateless AI tools that just reset every single time we hit enter?
An AI that actually grows with you and your project, that is a wild thought. Thanks for listening to this deep dive. We'll see you next time. So have you ever watched a pro play GeoGuessr?
Yeah.
It's honestly humbling to watch.
Oh, it's incredible.
They get dropped on some random dirt road. They spot like a specific type of fence post.
And suddenly they know they're in, rural Estonia.
Exactly.
But the really top-tier players, they do something else, too. They don't just go on vibes or intuition. If they see a sign, they want to cross-reference it on a map.
They verify.
They verify to confirm the road layout actually matches what they're seeing.
Right, and that's the gap we're diving into today. The paper is called Thinking with Map, and it tackles this massive limitation in AI vision models. The fact that until now, AI has basically been playing GeoGuess purely from memory without being able to, check the map.
That's a great way to frame it. The paper from Geolocalization, it points out that the existing large vision language models,
Like GPT-4 or Gemini?
exactly, they hallucinate so heavily in these tasks. They see a tower and think Paris, completely ignoring that the street signs are in Chinese.
Because they're just trapped in their own weights. They can't step out and check against reality.
Right. So the mission here was to build an agent that stops guessing and starts acting more like a detective, an agent with actual tools.
They call it the agent in the map loop.
Yep. So instead of just spitting out a coordinate, the model gets access to APIs. It can do keyword searches, look up specific points of interest POIs, and query map data.
But this isn't just give the AI internet access, is it? It's way more structured. That Xiamen example in the paper really made it click for me.
The Seikonomi bar case.
That's the one. So the AI looks at this street view image and it extracts the text Seikonomi bar from a sign.
And a standard model would just guess Japan because of the language.
Right, of course. But this agent runs a search query for that specific name and finds a candidate location in Xiamen, China.
But, and this is the critical part, it doesn't just trust that search result.
No, it looks back at the image and sees a Louis convenience store next door.
So it queries the map data again. Is there a Louis convenience store next to this specific Seikonomi bar in Xiamen?
It's looking for spatial consistency. It's verifying the visual evidence against the ground truth map data.
Precisely. It's reasoning, not just pattern matching. And to get it to do this, they used reinforcement learning. They rewarded the agent for using these tools efficiently to narrow down the search.
Okay, there's another layer here that I think is crucial, this parallel test time scaling. It sounds a bit dense, but it's basically how the model handles uncertainty, isn't it?
It is. Think of it like a chess computer exploring different future moves at the same time.
So instead of just one chain of thought, I see a sign, I'll search it, I'm done.
Exactly. It generates multiple reasoning paths all at once, in parallel.
So maybe path A focuses on the shop sign, but path B focuses on the road intersection layout.
Exactly right. It explores these different possibilities and then uses a verifier to sort of vote on which path led to the most logical and consistent result. It mimics how we eliminate possibilities.
But to prove this works, they couldn't just use standard data sets. We all know models like Gemini have already memorized the Eiffel Tower.
That's the data contamination problem in a nutshell. If the answer is already in your training data, it's not reasoning, it's just remembering.
So they built their own map bench.
Yeah, and it's a data set focused on dynamic, urban environments in China, which is smart because those places change so fast. It forces the model to rely on live data, not old memories.
And the results were, well, they were stark.
Oh, completely. When they compared their method against the closed-source giants like Gemini 3 Pro,
Even when Gemini had Google search access.
even then, this new method just crushed it.
I have the numbers here. On fine-grain accuracy, so pinpointing a location within 500 meters, they jumped from about 8% to over 22%.
Yeah. In computer vision, a 14% jump isn't an iteration. That's a generational leap.
Yeah.
It just proves that a smaller model with the right tools can outperform a massive model trying to brute force the answer.
It really shifts the paradigm from AI as an encyclopedia
To AI as a researcher, an AI that knows how to find and verify things.
But that capability brings us to a more provocative thought to end on.
I think I know where you're going with this. Privacy.
If an AI can take a grainy background detail from a selfie, a partial sign, a curve in the road, and use live APIs to triangulate the location within a few hundred meters, then security through obscurity is officially dead.
It really is. We used to think that unless there's a major landmark in the photo, you're anonymous. But now machines can read the spatial signature of our world better than we can.
It's a sobering thought for the next time you post a photo. Thanks for deep diving with us. You know that kid in calculus class who'd just stare at a problem, write nothing down, and then just scribble 42 at the bottom?
Oh, yeah. And somehow it's the right answer.
And it is. That's basically the state of a lot of deep search AI right now. We're getting these correct answers, but they often come from, shortcut exploitation or just lucky hallucinations.
Right. We have no idea if the model actually understood the question or just stumbled onto the solution, which is pretty terrifying if you want AI to be reliable.
Well, a new paper from Tsinghua University and Zipu AI called Chaining the Evidence is trying to fix that, to force the model to stop being that lazy student.
And actually show its work.
Exactly. They've developed this whole grading system, CAR-RR, and a new training framework called CGRPO.
And this really gets at the fundamental flaw in how we usually train these agents.
You mean the reward system? Because standard reinforcement learning, it's all about outcome rewards, right? It's binary.
It's just, did you get it right? Yes or no? And that's the whole issue. That kind of reward is way too sparse for complex reasoning.
That doesn't capture the process at all.
Not at all. So the AI just learns to scan for a few keywords, make a good statistical guess, and, ignore all the important details.
The paper has that Tybolite case, which is just a perfect example of this.
It's such a great example. So the prompt asked for the mass of an object from a meteor event, but it had all these constraints. It had to be over a Southeast Asian nation in the mid-2010s and linked to a prehistoric collision.
That is incredibly specific.
It is. And the standard AI model, it just saw Thailand and meteor, completely ignored the dates and context, and it just pulled a number from a totally different event.
The 36 tons number.
66 tons.
Yeah.
And it just so happened to be the right answer for the actual query, but the entire reasoning process was a complete hallucination.
It got the gold star for the wrong reason.
Precisely.
So that fragility is exactly what this new framework, CAR-RR, is designed to fix. It stands for Citation-Aware Rubric Rewards.
Yeah, it's basically a process grader. Instead of just checking the final answer, it breaks the entire thing down into 3 steps.
Okay, so what's the first one?
It starts with decomposition. The AI has to break the complex question down into like a checklist of smaller atomic claims.
So it's generating its own little premises that it has to go out and prove.
Exactly. Then it moves to the citation check.
Yeah.
For every one of those little claims, it has to find and cite a specific URL. It can't just say it was a meteor.
It has to prove which meteor and show the source.
Right. And finally, there's connectivity. All those facts, all those citations, have to form a connected graph, an evidence chain, that logically leads to the final answer.
It's like connecting the dots. You don't get credit for the last dot unless you actually drew the lines between all the other ones.
Which brings us to the training mechanism, CGRPO. This is really the engine that makes it all work.
And this is where it gets clever, because just grading the process isn't enough, right?
Right. CGRPO combines the old binary outcome reward with this new detailed rubric reward. But here's the twist.
Okay.
It assigns that rubric reward score only to the attempts where the final answer was also correct.
Wait, so let me get this straight. If the AI writes a beautiful, perfectly cited essay, but gets the final number wrong, it gets 0 points for its beautiful essay.
0. It prevents the model from becoming, a bureaucracy that generates perfect paperwork but fails the actual mission. You have to be right and you have to prove it.
And the results seem huge. The paper says that on benchmark like BrowseComp, these agents, they just stop taking shortcuts.
They do. They search deeper, they cite more pages, they actually verify the constraints before answering.
But the thing that got me was the generalization. They tested it on these open-ended PhD-level research tasks.
Deep research, yeah.
And the model wasn't even explicitly trained for that level of difficulty, was it?
No. But because it had learned the discipline of verification on simpler facts, it started applying that same rigor to much more complex problems. It was actually beating proprietary models.
Just because it had better study habits.
You could put it that way, yeah. It moves us from an AI that guesses to an AI that can build a verifiable argument.
Which kind of leaves us with a pretty heavy question, doesn't it? If an AI can prove every single step of its logic with a URL and a score, while we humans are still running mostly on, gut feelings.
At what point does the AI's black box become more transparent than our own minds?
That is the thought that's going to keep me up tonight.